In this lecture, we're going to talk about nth roots and rational exponents. We'll start by talking about the definition. The principal nth root of a real number a, where n is greater than or equal to 2 as an integer, is defined as follows. The nth root of a is equal to b means that a equals b raised to the nth power. So if you can find a number b when raised to the nth power is equal to the a value, b would be the nth root. In this definition, a and b are greater than or equal to 0 if n is an even number, and a and b can be any real number if n is odd. So when we look at the nth root, it's broken down as follows. The n is the index of the nth root. The root sign is called the radical, and the number underneath the root sign is called the radicand. Let's look at some examples. First, we have the fourth root of 16. In order to evaluate the fourth root of 16, we want to see if we can rewrite 16 as some number raised to the fourth power. And of course, we can. It's going to be 2 raised to the fourth power. The fourth root and the fourth power will cancel each other out, and so we'll see that the fourth root of 16 is equal to 2. So, negative 64 can be rewritten as negative 4 to the third power. And now, since the power and the index of the radical match, they'll cancel each other out, leaving us with negative 4. Finally, we want to look at the fourth root of negative 2 to the fourth power. Now, this example is a little bit different. Although we have a fourth power and fourth root, this is not going to cancel out to be negative 2. Because if we think about it, negative 2 raised to the fourth power, if we did that math, negative 2 times negative 2 is 4, times negative 2 is negative 8, times negative 2 again would give us a positive 16. So this is the fourth root of 16, which was our first example. So when we have a negative number underneath an even indexed radical, we need to take the absolute value when we cancel things out. So the fourth root and the fourth power do cancel out, but we're left with the absolute value of negative 2, which is 2. So in general, if we have the nth root of a to the n power, that will simplify just to be a if n is bigger than or equal to 3 and is odd, and we'll have that the nth root of a to the n power is the absolute value of a if n is greater than or equal to 2 and even. Next, we want to talk about simplifying radicals, but before we can actually simplify radicals, we need to discuss some properties that we'll use when we simplify radicals. So the first property says that the nth root of the product AB is equal to the nth root of A times the nth root of B. So if you have a product underneath the radical, you can split that up into two radicals using the same index. And it'll go the other way as well. If you have the square root of A times the nth root of a times the nth root of b, that can be combined to be the nth root of ab. The same is true for division. The nth root of a divided by b can be split up to be the nth root of a divided by the nth root of b. And then finally, if we have the nth root of a raised to the m power, we can rewrite that as the nth root of a raised to the m power. So the order that we evaluate those doesn't matter. We could do the power first, and then the root, or we could do the root first, and then the power. So let's do some examples where we simplify some radicals. The first that we're going to look at is the square root of 9 times x to the fifth. Now the strategy when we're trying to simplify radicals is to rewrite what's underneath the radical, the radicand, to rewrite it as the product of perfect squares. Since this is a square root, we want to try to write it as a product of perfect squares. So 9 is already a perfect square, and we could rewrite x to the fifth as x to the fourth times x. So now we have 9 as a perfect square and x to the fourth as a perfect square. Since 9 and x to the fourth are perfect squares, we could take the square root of those values and bring them outside of the radical. The square root of 9 is 3, and the square root of x to the fourth is x squared, so this gives us 3x squared times the square root of x, and that'll be our simplified answer, 3x squared times the square root of x. Next, we want to simplify the fifth root of x to the 10th times y to the fifth. Again, we want to try to write this as a product of perfect fifths this time. Since the index on our radical is 5, we want to rewrite the inside of the radical so that we have things raised to the fifth power. So we can rewrite x to the 10th as x squared raised to the fifth power, and y is raised to the fifth already, so that's already a perfect fifth. Now, since the terms underneath the radical sign are perfect fifths, we could go ahead and evaluate them and bring them outside of the radical, and that would give us x squared times y. So our simplified answer is x squared y. For our final example, we want to simplify the square root of 5x times the square root of 20x. The first step to simplifying this problem is to combine them into one radical. So since I have the square root of 5x times the square root of 20x, I can use the property of radicals. It states that the product of two radicals is the same as the radical of the product. So that's the square root of 5x times 20x, which would give us the square root of 100x squared. And now, just like our previous examples, we want to rewrite this radicand using perfect squares. Well, 100 is a perfect square, and x squared is a perfect square, so we don't have to do much to rewrite it. We can just take the square root of both terms. The square root of 100 would give us 10, and the square root of x squared would give us x. And so the simplified value of this problem would be 10x. Next, we want to talk about adding and subtracting radicals, and we can do this by combining like terms or combining like radicals. So for example, we want to combine 6 times the square root of 5 minus 4 times the square root of 5. Now notice that both terms in this problem have the same radical, the square root of 5, so I can combine the coefficients together and keep the same radical using the distributive property. So the square root of 5 will stay the same, 6 minus 4 will give us 2, and the simplified answer will be 2 times the square root of 5. Let's try another example. This time we have 9 times the cubed root of 24 minus the cubed root of 81. Now, we don't currently have like radicals, so we can't combine these yet, but we can use some of the properties of radicals to rewrite this problem and see if we can get the same radical in both terms. So since we're dealing with cubed roots in both terms, we want to see if we can rewrite the radicands, or what's underneath the radical sign, using a product of a perfect cube. So 24 we can rewrite as 8 times 3, and 81 we can rewrite as 27 times 3. Now 8 is a perfect cube, and 27 is a perfect cube, so we can evaluate that, take the cube root of these numbers, and move them outside of the radical. And this will give us 9 times 2 times the cubed root of 3 minus 3 times the cubed root of 3. Now we just need to simplify and combine the like terms. 9 times 2 is 18, so we have 18 cubed root of 3 minus 3 cubed root of 3. And now since we have the same radical, we can just combine the coefficients together. 18 minus 3 will give us 15, and so the simplified answer to this problem is 15 times the cubed root of 3. Next, we want to talk about rationalizing denominators. So when radicals occur in quotients, it's customary to rewrite the quotient so that the denominator does not contain a radical. So we're going to construct a little table here. If the denominator contains a factor, we want to multiply both the numerator and denominator by the same factor to remove the radical in the denominator. If the denominator has the square root of a number a, we're going to multiply both the numerator and denominator by the same thing, the square root of a. If the denominator has the square root of a plus b, we're going to multiply both the numerator and denominator by the square root of a minus b. Similarly, if we have the square root of a minus b, we'll multiply both the numerator and denominator by the square root of a plus b. And if we have the square root of a minus the square root of b, we'll multiply by the square root of a plus the square root of b. The key to these problems is to use the same numbers of the binomial, only switch the sign. So when I had a minus sign in between the square roots, I multiply both the top and bottom, the numerator and denominator, by the same values with a plus in the middle. And finally, this one is a little bit more tricky, but if I have the nth root of a raised to an m power, where m is less than n, I want to multiply both the numerator and denominator by the nth root of a to the n minus m. So the nth root of the base a raised to a power that when added to the previous power will give me a something that matches n. So let's do some examples where we rationalize the denominator. The first example is 2 divided by the square root of 3. Since I have a square root of 3 in the denominator, to rationalize this, I'll multiply both the numerator and denominator by the square root of 3. So when we multiply fractions together, we multiply the numerators together, and we multiply the denominators together. And that leads us to 2 times the square root of 3 divided by the square root of 3 squared. Well, if we take the square root of 3 and we square it, the square root and the square cancel each other out, and that leaves us with 2 times the square root of 3 divided by 3. So we've rewritten the quotient without a radical in the denominator. Now let's try the square root of 3 minus 1 divided by 2 times the square root of 3 plus 3. So this time, in order to rationalize the denominator, we multiply by what's called the conjugate. And again, that's just the same terms with the sign in the middle changed. So since my denominator was 2 times the square root of 3 plus 3, I'll multiply both the numerator and denominator by 2 times the square root of 3 minus 3. Again, when we do multiplication, we just multiply across with the numerator and with the denominator. And since these are binomials, we can use the FOIL method for both of those. So our numerator becomes 2 times the square root of 3 squared minus 3 times the square root of 3 minus 2 times the square root of 3 plus 3. And our denominator becomes 2 times the square root of 3 quantity squared minus 6 times the square root of 3 plus 6 times the square root of 3 minus 3 squared. We'll begin by simplifying our exponents. So we're going to evaluate those square terms. So that leads us to 2 times 3 minus 3 root 3 minus 2 root 3 plus 3 divided by 4 times 3 minus 6 root 3 plus 6 root 3 minus 9. Notice that the denominator we have minus 6 root 3 and plus 6 root 3. Those will cancel each other out. So the next thing we're going to do is we're going to simplify the multiplication in our problem. That leads us to 6 minus 3 root 3 minus 2 root 3 plus 3 divided by 12 minus 9. And so our final step will be to combine like terms in both the numerator and denominator. And so our numerator simplifies to be 9 minus 5 times the square root of 3, and our denominator simplifies to be 3. Let's look at one final example of rationalizing the denominator. This time we have 5 divided by the cubed root of 16. So to begin with, let's rewrite this to make it a little bit easier to deal with. We know that 16 can be rewritten as 4 squared. So this is 5 divided by the cubed root of 4 squared. And if we think about that, that means that we have 4 times 4 underneath the cubed root in the denominator. If I want the cube root to cancel out, I need to have 3 4's down there. So to do that, we're going to multiply both the numerator and denominator by the cubed root of 4. Now remember, with multiplication, we'll just multiply straight across. We'll multiply our numerators together and our denominators together. And that'll lead us to 5 times the cubed root of 4 divided by the cubed root of 4 cubed. Now, since the cubed root and the cube are both in the denominator, they will cancel each other out, leaving us with 5 times the cubed root of 4 divided by 4. For the last part of this lecture, we want to talk about rational exponents. So if a is a real number and n is greater than or equal to 2 is an integer, if we have a raised to the 1 over n power, the denominator of the fraction in the exponent tells you the index of the radical. So a to the 1 over n is the same thing as the nth root of a. Similarly, a to the m over n would be the nth root of a to the m. So again, when you have a rational exponent, the numerator of the exponent gives you the power of your base, and the denominator of the exponent gives you the index of the radical. So let's look at an example. First, we want to evaluate 4 raised to the 3/2 power. So the first thing that we want to do is rewrite this, breaking up the rational exponent. So remember, the numerator of the exponent tells us the power on our base, and the denominator tells us the index of the radical we should use. So since we had 4 raised to the 3/2 power, that's the same thing as the square root of 4/3. Now we can just evaluate these. It doesn't matter which order we go in. We can do the square root first, or we can do the power first, but we do need to evaluate them. So I'm going to do the power first. What's 4 cubed? 4 cubed is 64. So now we have the square root of 64, which we know is 8. Here's another example. 27 divided by 8 raised to the 2/3 power. So again, the numerator of the exponent tells us the power to use, and the denominator tells us the index of the radical. So since there is a 2 in the numerator, we're going to square this, and the 3 in the denominator means use the cubed root. So we can rewrite this as the cubed root of 27 over 8 quantity squared. And again, the order that we evaluate these in doesn't matter. We could square first, or we could take the cubed root first. I'm going to go ahead and take the cubed root. So we can take the cubed root of each term. What's the cubed root of 27? And what's the cubed root of 8? And so that'll give us 3 over 2. So we have 3 over 2 quantity squared, which simplifies to be 9 over 4. Next, we want to do an example where we simplify expressions with rational exponents. So this is similar to some of the things that we've done in the past. What we want to do is we want to rewrite this so that each base is represented only once. So we want to combine the powers together using rules of exponents. So our problem is x times y raised to the 1/4 power times x squared times y squared raised to the 1/2 power times x squared y raised to the 3/4 power. The first thing that we want to do is get rid of the parentheses by distributing the exponents throughout. So in the numerator, we'll have x to the 1/4, y to the 1/4, and we'll have x to the 2/2, y to the 2/2. In the denominator, we'll have x to the 6/4 times y to the 3/4. Okay. The next thing that we want to do is we want to start combining the exponential expressions that have the same base. So we'll start in the numerator. We want to combine the x's and we want to combine the y's. So remember, to combine exponential expressions that have the same base, you add their exponents together. So in the numerator, we'll have x to the 1/4 plus 2/2 times y to the 1/4 plus 2/2 divided by x to the 6/4 times y to the 3/4. So we just need to simplify this. We can add 1/4 and 2/2 by creating a common denominator of 4. So that'll be the same thing as x to the 1/4 plus 4/4, which gives us 5/4. So this becomes x to the 5/4 times y to the 5/4 divided by x to the 6/4 times y to the 3/4. Again, we want to combine the terms with the same bases. This time, using division, we subtract the exponents. So that'll give us x to the 5/4 minus 6/4 and y to the 5/4 minus 3/4. These already have common denominators, so we can just combine them to give us x to the negative 1/4 times y to the 2/4. Now the final thing that we want to do is we want to clean this up a little bit. We can simplify 2/4. And remember, when we're writing these problems, we don't want to have negative exponents, so we can move the x term into the denominator, giving us y to the 1/2 divided by x to the 1/4. Next, we want to do an example where we look at writing expressions as a single quotient. So we have x plus 1 to the 1/3 power plus x times 1/3 times x plus 1 to the negative 2/3 power. And we want to combine this into a single quotient. So the first thing we want to do is rewrite things so that there are no negative exponents. So our first term is fine, x plus 1 to the 1/3 power, but the second term we need to do a little bit of work. So the x can stay in the numerator, and the 3 will be in the denominator, and x plus 1 to the negative 2/3 tells us that we could write x plus 1 to the 2/3 in the denominator. Now in order to add these together, we want to have a common denominator. So our common denominator will just be 3 times x plus 1 to the 2/3 power. So to get the common denominator, we'll need to multiply the first term by 3 times x plus 1 to the 2/3 over 3 times x plus 1 to the 2/3. Now remember, when you multiply exponential expressions together, if they have the same base like this does, you just add their exponents. So 1/3 plus 2/3 will give us 1, so this simplifies to be 3 times x plus 1 over 3 times x plus 1 to the 2/3 power plus x over 3 times x plus 1 to the 2/3 power. So now that we have the same denominator, we can just add these together. That gives us 3 times x plus 1 plus x all over 3 times x plus 1 to the 2/3. And then we'll simplify the numerator by distributing the 3 and then combining like terms. So when we distribute the 3, that gives us 3x plus 3 plus x. And if we combine like terms, that gives us 4x plus 3. So the simplified quotient is 4x plus 3 divided by 3 times x plus 1 to the 2/3 power.